Hello and welcome. In this video, we're going to be looking at AP Physics 1 free response questions review for Newton's laws. Remember to pause and rewind the video as needed. Let's begin. In problem 1, for each case, draw and label the forces, not components, acting on each object. Each arrow must start as on a white dot and be straight. Then one or more equations relating the forces on the subject. Finally, rank the three forces in the blanks. Acceptable labels are F sub W or F sub G or mg, that would be for weight, F sub n for normal force, big F sub little f for friction, big F sub T for tension, and big F sub applied for an applied force. Let's begin. Letter A shows a car slowing down, and it's indicating that there are three forces that are supposed to be acting on this car. So the first thing we need is, from the center of the mass, we're going to draw the weight. Weight equals mg. That should be balanced by a normal force. Make sure they're equal length. And slowing down the car, of course, would be friction. Now, friction is normally equal to mu times normal force. Since we're not actually solving a problem, we don't need to worry so much about that this time. Your basic net force equation is equal to MA, but we could also view it as causing force minus opposing force equals MA. Now, what's the causing force? What's the opposing force? Well, in this case, we're slowing down, but you're going forward. That means the acceleration is going this way. Even though the velocity is going forward, the acceleration opposes the velocity. So which force goes in the direction of acceleration? Well, that would be friction. There is no opposing force. So in this case, friction equals MA. Now, in the balanced forces, of course, would be the forces in the y direction. That's using Newton's first law. So we use Newton's second law for the net force equation. Use Newton's first law to balance the forces. Newton's first law just simply states that the net force equals 0, or balance your forces. So in this case, it's F sub n equals mg. Now, mg and normal force are equal, but since normal force is, or friction rather, excuse me, is a fraction of the normal force because it's mu times normal force, friction will always be shorter or smaller than normal force. Letter B. In letter B, we've got a child sliding down at a constant speed. Again, three forces acting on the child in this sled. So let's draw a force going straight down. We're going to have a normal force going straight up out of the plane. Okay, and you're going to have friction going up the plane. Now, it said no components, right? No components. But here's the thing you need to know. When you have a force applied at an angle, over to the side, somewhere over to the side, you make sure you redraw the problem showing the actual components. So we may not draw the components on here, but over to the side, let's make sure we have accounted for all the forces and their components. So we've got the weight going straight down. You've got the normal force going out of the plane. You have the components of the weight going into the plane, like in this direction. and you have a component going parallel to the plane. So you have perpendicular to the plane, parallel to the plane. And of course you have friction. Okay, now why am I drawing this? Well, this angle here is the same as the angle of the hill. This would be mg times the cosine of the angle. The force pointing downhill would be mg times the sine of the angle. This is what we need to be able to answer these questions here. The balanced force equation would be the one in the y direction, and you can see the normal force going up is equal to mg cosine going down. But since we're going at a constant speed, we also have balanced forces in the horizontal direction too. And that would be friction going to the left equals mg sine going to the right. Okay, now which forces out of these three forces here, okay, would be the largest? Well, the weight would be the largest, and here's how we can reason this out. You know friction is going to be the smallest because it's a fraction of normal force. Then you know normal force is going to be a fraction of the weight because it's equal to weight times the cosine of theta. The cosine of theta makes it less than the weight. So the weight is the greatest force, followed by the normal force, followed by friction. Okay, we have a box moving with constant speed up the hill. So you've got a force going straight down from that white dot. There's the weight equals mg. And you've got your normal force. Okay, then you have your friction. Okay, and then you have your applied force. Now, how long do we draw the applied force? Well, you've got mg sine going down the hill here, and this force, it should be the sum of both of those lengths. In other words, about that long. And that would be F applied. And actually, I made a mistake on the directions here. Remember, all forces need to be drawn from the white dot. So normally friction is drawn from the surface, but here in a free body diagram, you have to remember to draw it from the white dot. So I'm just going to move all the friction diagrams, the friction parts, to the white dot itself. There we go. There we go. Again, we're not allowed to draw components on this diagram. So over to the side, we're going to have a small diagram showing components. So we've got normal force, we've got weight, we have mg cosine here, we have mg sine here, we have friction, and you have applied force. Of course, normal force. Okay, so what are our balanced forces equations? Well, we can start with up equals down, and the normal force going up is equal and opposite to the mg cosine of the angle. The balanced forces horizontally would be F applied going up the plane is equal to friction and plus you have two forces going down the plane, mg sine. Okay, if we rank the forces, we can see that again, the smallest one has to be friction because friction is a fraction of the normal force. I'm going to start there. Friction is a fraction of the normal force. But then what about between F applied and the weight? Well, F applied is the sum of the friction and the mg sine going downhill. Well, the mg sine plus the friction is not large enough to be greater than the weight. The weight is still the greatest force. F applied is the second greatest, then normal force, then friction. Well, in letter D, a block is held against the wall, okay, at rest. So at rest, we're not accelerating again. Balanced forces again, okay, but you should expect 4 forces going on here. Okay, 1, we should expect our weight still going straight down. Okay, you should expect force applied. Force applied is going to be larger, okay, than the weight. This is the one time that weight is not going to be the greatest force going on here. Okay, why is force applied going to be a larger weight? Because normal force, which balances it, needs to be exactly the same. Okay, so normal force equals F applied. And why is that important? Because friction going up the hill is equal and opposite to the weight. And remember, friction is always a fraction of the normal force. So the smallest one is the weight, but that's equal to friction, which is less than normal force, which is equal to force applied. Well, in question E, we have a man and a bicycle go over a hill at a constant speed. Well, now we should be thinking centripetal forces. Well, centripetal forces are unique because now we're looking at causing force minus opposing force equals MAC, centripetal acceleration, or you could write it as mv squared over r. The causing force would be those forces pointing into the circle, so that would be in, and then the opposing forces would be the ones pointing out of the circle. So if we draw the forces acting on the man, there's really only 2 of them. You've got the weight going down, and you've got the normal force going up. Please do not say that normal force equals weight. That is not true. You are changing direction. We are centripetally accelerating. Okay, what that means is causing force, forces into the circle minus forces out of the circle are equal to mv squared over r. So forces into the circle would be weight, minus forces out of the circle, that would be normal force, are equal to mv squared over r. Ranking those forces, mg has to be greater than the normal force because you're curving in that direction. You're always curving in the direction of the greater force. Well, in situation F, we have a satellite orbits the Earth, okay, and there's really one force acting on this thing, and that would be the weight, Fg. But recall, Fg, we're talking about 2 masses, right? M1, M2, right, is equal to big G, M1, M2 over R squared. Yeah. So what's the net force equation on this? Well, it would be big G equals MA. But remember, it's MAC. Gravity is a centripetal force. This is the path, and it's pointing to the center of the circle. So mv squared over r. Now, you must be prepared to make this kind of substitution in certain free response problems. And that is taking Fg is equal to mv squared over r and substitute for Fg with big G, M1, M2 over r squared equals mv squared over r, where this m is usually the same as the second one. And this is usually the mass of what's being orbited. This cancels one of those factors, and we're left with big Gm over r equals v squared. Something to consider for uniform circular motion problems involving gravity. In problem 2, it says Newton's third law is also known as the law of action and reaction. The law says when A pushes B and B pushes A with the same amount of force but in the opposite direction, A common misconception is that action is cause and reaction is effect. It turns out that action is a cause and reaction is another cause, each having its own effect. Example: a child jumps and lands on a trampoline. Not action and reaction. The child lands on the trampoline, the child pushes down on the trampoline, and the trampoline bends downward. The bending downward is the effect because of the push. Now, if we state it differently, we could say the child exerts a downward force on the trampoline. That's the cause. This bends the trampoline downward. The trampoline, so the child is mass 1, the trampoline is mass 2. Remember, Newton's third law deals with the interaction of forces between two masses, not one. The trampoline exerts an upward force equal and opposite on the child. That's the reaction. The effect of that would be the child's downward motion slows down to a stop or reverses in the other direction. Now let's try. We're going to take each situation and we're going to identify the cause, the reaction, action-reaction causes, and the effect of each one, effectively breaking down Newton's third law. In part A, a horse and a wagon are initially at rest. The horse begins to accelerate by walking forward. Well, the cause in this right here, two causes rather. What's the cause from the horse? The horse pulls on the wagon. The wagon pulls back on the horse. Let's go back to the action horse. The cause of the horse pulling on the wagon means that the wagon begins to move forward. The reaction effect on the horse itself, if the wagon pulls back on the horse, this means the horse does not go forward as quickly. As it would without pushing on the wagon or pulling the wagon. Part B. A heavy car collides with a light car. The cars don't stick together. The heavy car pushes the lighter car forward. The effect on this, of course, is the light car moves forward. The light car pushes the heavier car backward. The effect of this is that the heavy car slows down as a result of the lighter car pushing back on it. Letter C. In part C, it says a helicopter hovers over the ground. The grass on the ground lies flat due to the airflow under the helicopter. We're going to take a look at the differences between the forces acting on the helicopter and the air. Those are the two different masses. So what does the helicopter do? Well, the helicopter pushes the air downward. the air pushes up on the helicopter blades. So there's your action-reaction. Let's talk about the cause and effect of each one. Well, if the helicopter is pushing the air downward, the air flows downward. It's going to be pushed downward. And the effect of the air pushing back up on the helicopter is the helicopter remains hovering. In problem 3, we are going to encounter various scenarios with various Newton's law implications. Let's take a look at each one. Part A. A spring is attached to the ceiling of an elevator and a block of mass m is suspended from a spring. In case A, the elevator moves upward with a constant speed of 5 meters per second. In case B, the elevator moves downward with a constant speed of 10 meters per second. Will the spring be stretched more in case A or case B? Well, in both cases, you're moving with constant velocity upward, constant velocity downward. So in both cases, the mass and the spring force, since it is the same mass, are equally stretched. So we could reason out as follows. In both cases, the elevator moves with constant velocity. Which of course means acceleration equals 0. This means the block's weight balances the spring force. Pulling up on the block. Thus, each spring will be stretched the same amount. Again, each spring is being pulled on by the same mass, therefore the same weight. Since you're moving at a constant velocity, each spring is going to stretch the same. In letter B, a loaded barrel is attached to a rope that passes an overhead pulley and is tied to a ring on the floor. Linda, a construction worker, plans to untie the rope from the ring, pull on the barrel to lift 1 meter high, then retie the rope. Linda's mass is 80 kilograms. She is capable of lifting twice her weight. The loaded barrel has a mass of 120 kilograms. Explain what is wrong with Linda's plans. Well, if we examine what's going on here, if she were to pull on the rope, tension would be pulled up in this direction. But the barrel itself has a weight of 1,200 newtons pulling down on it. And it would have tension pulling up that same way. The problem with this is that the barrel, Linda's weight, is only 800 newtons. The barrel is heavier than she is. Linda would be lifted off of the floor. Part C. Graphs are shown of the velocity versus time of two identical trains on a straight track. The positive velocity represents eastward travel. Both graphs have the same scale. On each graph, t equals 2 seconds is indicated with a dot. A student makes the following observations. Quote, I think that B has the greater net force acting on the engine at time equals 2 seconds because the net force on A is 0 at that time. What is wrong with the student's statements? What could the statement be corrected? Now, if you look, both of these, what's wrong with this statement is that the net force on A is not 0. Okay, that's the wrong part of the statement. How could it be corrected? If you look at each one of these, both of them are velocity versus time graphs. And the slope of a velocity versus time graph equals acceleration, which relates to the net force, right? Net force equals mass times acceleration. Therefore, if you look, both graphs have the same slope. Therefore, both trains have the same acceleration. Both graphs have the same slope, which means they have the same acceleration, which means they have the same net force. The difference in these graphs is that the train here started from rest and speeds up. This train here starts westward, slows down to a stop 2 seconds later, most likely is moving backwards to the west, slows down 2 seconds later, and then speeds up going forward. All in all, it's still the same positive acceleration. All right, in part D, a person using a rope pulls a heavy slab across a rough horizontal surface at a constant speed. I'm going to stop right there. If we're pulling with constant velocity, that means we need to use Newton's first law to analyze this, which means we are going to balance our forces. Balance our forces in the x and y direction. Let's continue. The person's applied tension is T. The object's weight is W. The normal force is N, and the friction is little f. And they're all drawn from the center of the mass here. A student observes this situation and states, quote, I think that T equals F and that W equals N. Because F is equal to mu times normal force and mu is less than 1, the correct ranking of the forces must be weight is equal to normal force, which is greater than tension is equal to friction. Explain what is wrong and what is right about the student's observations. Then write a complete sentence relating all the forces. Okay, let's start what was incorrect. For one, what's incorrect about this is that tension does not equal friction and normal force does not equal weight. So we're going to start there. Let's go to the picture. You can see tension is applied at an angle theta. So we need, ladies and gentlemen, vector components. This side here would be t cosine of the angle. This side here would be t sine of the angle. So if I start here, tension does not equal friction, rather tension cosine of the angle equals friction. And if I solve for tension is equal to friction divided by the cosine of the angle. Now, since the cosine of the angle is a decimal less than 1, friction divided by a number less than 1 makes the tension greater. It means tension is greater than friction. Similarly, with the normal force, we're going to go forces up equal forces down. Turns out there's two forces going up, not just one. Where a lot of students make the mistake is they automatically just put those forces equal. Well, that's not going to be true if you have a third force in there. So you have two forces going up equal to that one force going down. So this should be normal force plus t sine theta equals weight. I'm going to solve for normal force in this case. Normal force is equal to the weight minus t sine theta. Since you are subtracting something from the weight, it must mean that the normal force has to be greater than the weight. Rather, that's the opposite. If we're subtracting from the weight, the normal force is going to be a smaller number, not the weight. And this should make sense because if we're pulling at an angle off the ground, it means the force coming from the ground should be less than the weight pulling downwards. So tension is greater than friction, normal force is greater than weight. Okay, now what is correct in this statement? What's correct is that friction is less than normal force. Friction will always be less than normal force. Okay, now let's write a correct statement about this. And we're comparing all four of these. So we know that friction will be less than normal force. So friction is less than normal force. We know that normal force is less than weight. And we know that tension is going to be greater than friction. And finally, part E. A light rope connects a 5 kilogram block on a horizontal surface to a 2 kilogram hanger. The 5 kilogram block is on a rough surface, horizontal surface, and someone gives the 5 kilogram block a sharp push to the right, this way. The free body diagrams are shown, indicate the forces after the push. The four students argue over the force diagrams. A, the 2 kilogram free body diagram is wrong. The forces should have the same magnitude. B, the problem with the 2 kilogram free body diagram is the upward force should be stronger than the 2 kilogram since the 2 kilogram moves upwards. And C, the 2 kilogram is fine, but the 5 kilogram free body diagram has friction in the wrong direction. All right, so let's true-false these, okay? In part A, it says the 2 kilogram one is wrong. The forces should have the same magnitude. No, they should not. If we are given a force, a net force in this direction, it means we're going to accelerate this way, it means we're going to accelerate this way. It actually means that this should be longer than this, but they should not be equal. They should not be equal. That's false. Part B, the problem with the 2 kilogram free body diagram is the upward force should be stronger than the upward force. Well, here's the thing. This one is given a push, and actually I drew the acceleration incorrectly. It's given a push, but it's given a sharp push, but it's not given a continuous push. So it's just given a push. What it basically means is as soon as you give it the push, this object may move this way, but it's going to slow down. So if it's moving forward, slowing down, means the acceleration opposes that, means the acceleration is actually going the opposite way. So indeed, this is correct. This should be longer than this because the acceleration is going in that direction. So part B is wrong because the upward force should not be stronger. And student C, the 2 kilogram block is fine. Yes, it is, because but the 5 kilogram block has friction in the wrong direction. True. If the 5 kilogram block, if the motion is to the right, friction should be acting to the left, and it's not. It's acting to the right. So indeed, that one is true. So let's summarize what's going on with these student arguments. Student C is correct. The 5 kilogram block moves to the right, so friction should be directed to the left. Move this over a little bit. There we go. Student A is incorrect. The system is accelerating so the forces cannot be balanced. And lastly, student B is incorrect, the 2 kilogram block is slowing down, going upward. This means the acceleration is opposite and is going downward. This should make the weight a longer force vector than the tension. Since weight is the causing force of the acceleration. Again, ladies and gentlemen, please remember to pause and rewind the video as necessary. Thank you.